So let's say this is part A. What is the probability, or sorry, what was I, oh no. I want to roll a die, sorry. And let's do it 7 times. Not that it matters. Roll a die 7 times. Sorry about that. We already did flipping coins last time. What is the probability that it lands, or that, well, you get exactly 4 5s? Okay. So if I roll a die 7 times, right? Every sequence of possible outcomes is equally likely, right? So it's equally likely if I get, 1, 1, 1, 1, 1, 1, 1, or 2, 3, 7, or there aren't any 7s on a die. 2, 3, 5, 1, 2, 2, 3, or whatever, right? So every outcome is equally likely. So this comes down to a counting problem. So maybe I'll ask, first, how big is our sample space here for this experiment? So how many possible outcomes are there? Okay, so I think a few people talked at the same time, but I'm sure somebody said 6 to the 7 at some point. Right, because yeah, each roll has 6 possibilities. You're doing it 7 times, so 6 possibilities times 6 times 6 times 6, and so on. Okay. Now, so our answer for this probability it's going to be a fraction, and we already know what the bottom of the fraction is. So the question boils down to how many outcomes have exactly 4 5s? So suppose I'm going to have 4 5s. How many ways can I choose which rolls are 5s? So I'm doing 7 rolls. How many ways can I choose which ones are 5s? Yeah. Yep. But now we have to be a little bit careful here because, so if this was like a coin flipping problem, if we were talking about heads and tails, once you choose the heads, then you already know the rest of them are tails and you've kind of determined everything. Here we need to be careful because, so this is the number of ways to choose the 5s, which is what I was, yeah, so that's right, that's exactly what I was asking for. And that now you need to think about, suppose I choose the 5s to be here, 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 let's say, and here. How many choices are there now for this roll? Yeah, it's really tempting to write 6 because, well, it could be 6 different things, but the thing is, it can't really be a 5 because if it was a 5, then I've got another 5, and you're supposed to have exactly 4 of them, right? So these have 5 choices, right? It can be anything but a 5. If it's a 5, then we're going to have 5 5s. So, and again, I've got 5 choices, 5 choices. So you're going to want a 5 cubed here. And I think that gives you something like that. So you've got like a 1.5% chance or 1.6% chance. Okay. Any questions about that? Okay. Here's a famous problem, which is kind of a, well, it's often called the birthday problem or the birthday paradox. Although it's not exactly a paradox, but it's something which seems very counterintuitive. So, okay, let's make an assumption. Let's suppose that every day of the calendar year, so, is equally likely to be somebody's birthday. Like, so suppose, and this is probably not true because, I don't know, for various reasons, maybe there's more people born on, I don't know, April the 13th than there are people born on December the 5th or something. I have no idea, but let's just assume, to make life simple, that, you know, if I pick a random person, they're equally likely to be born on any day of the year. And let's ignore leap years, so there is no February 29th, let's say. So suppose each day of the year is equally likely to be someone's birthday if you pick a random person. And again, this probably isn't reality, but it's probably pretty close, right? Okay. So how many people do you need? Like if you pick people, suppose I just pick people randomly from this room, and I say, you know, go to another room or something. How many people would I need to pick to have a bigger than 50% chance that two people have the same birthday? So you're kind of saying something like, yeah, intuitively, I mean, you would at least think this has got to be, it's got to be, I mean, definitely if you've got more than 365 over 2, it's gonna be hard for them to all have different birthdays. That is, I mean, that is a guess that naturally comes to mind, yeah. You would at least think it'd be like, well, I don't know. Who thinks it's, okay, let's say our options are less than 50, bigger than 50. Well, let's say, less than 50, between 50 to 100, 100 to 150 days, or let's say more than 150 days. Okay, I'm not going to actually count your hands, but who thinks it's less than 50 people? I mean, who thinks it's between about 50 to 100 people range? Who would think it's about between 100 and 150? And more than 150? Yeah, you've got, I mean, it's reasonable, completely reasonable intuition, but most of you are wrong. It's in this range. Yeah, it's something in the 20s. So let's do the calculation and see what happens. But it's very, very, very counterintuitive. I would have probably said, if I didn't already know the answer, I probably would have said something around here, but I mean, I don't know. But so the answer definitely isn't 365 over 2. Okay, so, well, what is the probability? So let's say, suppose you have R people. So R random people. What is the probability that they all have different birthdays? Ooh, that's not good spelling. Okay. If I take R people at random, right? Let's say I kind of think of them as kind of like a, well, yeah. How many, what's my sample size? Like how many different sequences of birthdays could I have? Yeah. Yeah. Exactly, yeah. So it's a good sample size. And then how many ways could I pick different birthdays for every person? Like, so for the first person, they've got 365 choices for birthday. Like it doesn't, it could be anything, right? But if I want to choose different people with different birthdays or different birthdays, a sequence of R different birthdays, for the second person, I only have 364 choices, right? So like this is picking any sequence of birthdays where we don't care if they're the same or not. And now we're saying how many ways can I pick different birthdays? And for the third person, it'd be 363 because it has to be different from these two. And then you go all the way down to, if you think about it, it's 365 minus R plus 1. However, okay, I've kind of done this in a, wait, is that the, yeah, that's the right thing. Although you could also just say that this is P365 R over 365 to the R. So really that's what I've kind of, that's what I basically written there. And if you plug in numbers, you'll see that if I plug in 23, for R, then you get a number something less than 0.5. So therefore, if I've just got 23 people, the chances that they all have different birthdays is less than 50%. But that means the probability that 2 of them have the same birthday is bigger than 50%. Because this rule of complements, right? The probability that 2 people have the same birthday is 1 minus the probability that they all have different birthdays. So if this is less than 50% probability, then the probability 2 people have the same birthday is more than 50%. And so 23 is the number. If you put in R equals 22, it's a little bit bigger than 50%. So 23 is when it changes. So yeah, I'm pretty sure 2 of you have the same birthday in this class. Probably multiple of you have the same birthday. Okay, is that, any questions about that? Yeah. Yeah, it's, I mean, basically you can just try numbers until you get something less than 50%, and yeah. So I just already knew this, but if you're trying to solve this problem yourself, you might throw in a number and see what it is and adjust until you get the right thing. But any other questions? Okay. I wonder who has the same birthday in this class. Yeah. Okay. I mean, this is only saying like bigger than 50% chance, so there's still a almost 50% chance no one would have the same birthday if you had, 23 people. Okay. Let's do another example. So suppose a drunk person so this is going to be one of these problems where we're kind of walking in a grid. So the drunk person is going to walk from 0, 0 to 5, 4. So it walks from 0, 0 to 5, 4. But every time it takes a step, it either walks one direction up, 1 unit up, or 1 unit to the right. Okay? And when I say that they're drunk, what I mean is like, every step they randomly either go forward or they go to the right? So there's an equal chance at every step that they go up or they go right. So they take steps 1 unit up or 1 unit right, each with probability 1/2. So now my question is, what's the probability that their walk goes through the point 3, 1? So what's the probability that the walk passes through the point 3, 1? So is the question clear? Start here. We either go this way or that way. Then we, if we go here, let's say, we either go up or right. And we want to know what's the probability that at some point they come to this point and then they continue up to 5, 4. Okay. So again, my answer is going to be a fraction, right? Basically, every way of walking from 0, 0 to 5, 4, by only taking steps up or right, all of those paths are possible, right? And they're all equally likely. It's the probability of, let's say, going up, 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 right. Well, that has probability like, this step has probability half, a half, a half. So like, that's the same probability as taking right you know, 5 steps to the right and 5 steps up, or going right, up, you know. Every different path has the same probability, right? So the question, for finding the denominator, we just want to figure out how big is our sample size. So how many paths are there from 0, 0 to 5, 4? We did one problem like this before, one example, but it was a few classes ago. Yeah. I see that you're, yeah. 20 would be the area of this square, but yeah. So for any given path, the probability of doing that path would be 1/2 to the power of 9, but that's, so what we're asking for here is the how many paths there are. Yeah. Actually, when I say that every path would have that probability, I'm actually slightly wrong about that. You have to be a bit careful. Yeah. So sorry, I may be actually describing this problem wrongly. Because here's the thing. Suppose I take my 4 steps up. At this point, I don't actually have an equal probability of going right or up. Because if I go up, I can never get back. And we're saying he goes from 0, 0 to 5, 4. So I'm sorry, this is not quite right. So he takes one unit up or 1 unit right in such a way that every path is equally likely. So it's a little bit more complicated. But that might, I understand this is probably going to introduce a bit of confusion here, but yeah. Maybe, but where did that come from? Yeah, no, not quite. So it will involve some kind of 5 and 4 factorials in some way. But here's the thing. So to compute the number of paths from here to here, here's the trick. You recognize, oh yeah, sorry. Pretty close, 9 choose 5 or 9 choose 4. Yeah, I figured you must mean 9, yeah. Yeah, so it's going to be 9 choose 5 or 9 choose 4. They're the same number anyway. Here's the principle here. You know that if I go from here to here, you're going to take 9 steps, right? Because I start at 0, 0, I need to end at 5, 4. So 5 of your steps have to be to the right, 4 have to be up. So you must take 9 steps. And then choosing a path just means choosing which of those steps go right and which ones go up. Right? So if I kind of you can think of it as a sequence like up, up, right, right, up. You know, so this kind of sequence of ups and rights would correspond to a path where I go up, up, right, right, up, right, right, up, right. So if you think about it, there's always going to be 9 steps, and you just need to pick which ones are ups and which ones are rights. So let's say 9 choose 4. Doesn't matter if you write 9 choose 4 or 9 choose 5. So now we have to count paths from 0, 0 to 5, 4 that go through this point, which actually follows the same principle, but it's a little bit more complicated. So here's the thing. If I'm going from here to this point, from here to here, going through this thing, that's the same as taking a path from here to here, and then a path from here to here. So it's a 2-step process, right? So you want to take how many paths are there from here to here times how many paths are there from here to here. And so from here to here, it's the same idea as before. It's going to be 4, choose, let's say, 1. Because from here to here, you take 4 steps and only one of them goes up. From here to here, how many steps am I going to take? I think I'm going to take 2 to the right and 3 up. So 5 steps total. And 2 of them are going to be to the right. Yeah, 5 choose 2 or 5 choose 3, whichever you prefer. Yeah, so that ends up being your answer. Yeah. It's the same as 4 choose 3, yeah. So generally, n choose r is the same thing as n choose n minus r. Yeah. Any other questions? Yeah, oh, sorry. You could totally mix and match, yeah, because it'll give you the same numbers. So like, if I just make that a 3 and I make that a 3, and you can mix and match. It doesn't really matter. Yeah. Choosing four spots, 4 places to go up or whatever is the same thing as choosing 5 places to go right, because everything that's not an up will be a right. So. Okay. Let's move on to section 6.4. Okay, so this is a section we're going to spend a lot of time on because it's a tricky one. So let me kind of vaguely tell you what's the idea of conditional probability? Basically, like the philosophy here is that suppose I'm doing an experiment and I want to know the probability of something happening. If I already have some prior information, then that can change the probability in some sense. So sometimes having additional information affects the probability of certain events. Okay. That's a very vague description, but let's do a sort of simple example. So roll a die. So what is the probability that you get a 6 with no additional information, Yeah, 1 over 6. It's not a trick question, But here's the thing. Imagine you roll a die, and you don't look at it, but I look at it, and I tell you that die is an even number. So roll a die. someone else tells you it is an even number. And like, let's say this person doesn't lie, right? So you know they're telling the truth. So now what's the probability that it's what's the probability that that's a 6 after that person told you this information? Yeah, 1/3. Okay. So this kind of gives you this kind of concept. Sometimes if you're given extra information, it sort of warps the probability, right? It changes the probability of different outcomes. So basically, if you're computing the probability of an event, and you already know that some other event holds, then it might change the probability of your event. So the way we would kind of write this in kind of mathematical notation is like the probability, it is a 6. Then we write a line. So this line, you kind of say given, or given that, or conditional on the fact that it is even is 1/3. So this line means we're conditioning on, like we're assuming this is true. If you assume this is true, then the probability is it's 6 is 1/3. Right? Any questions about that? So that's just an example, but now we'll look at how it works more generally. So given two events, E and F, the conditional probability of E given F is, so the notation is like this. And there's a formula for it, which is probability of E intersect F divided by the probability of F. Okay. Let's double check our intuition using this formula. Like this 1/3 thing, we were just sort of intuitively thinking, well, that's got to be the right answer, right? There's 3 possibilities that are even numbers. But let's check this formula. So suppose E is the event that a die roll is a 6, and F is the event that it is even. So let's start with the denominator here. So probability of F, I guess, we can tell it's going to be a half, right? Well, let's do this really formally and say it's the size of your sample space, which is 6 on the bottom, and then on the top you've got the number of even outcomes, right? So it's a half. Can anyone see what probability of E intersect F is going to be? It's kind of a weird one. So it's the probability, it's a 6 and it's even. Yeah, 1 over 6. It's kind of confusing though, because like if it's a 6, you already know it's even. So the F here doesn't really affect anything. Like in this case, E intersect F would just equal E, because if I know it's a 6, then it's already even, so it doesn't make a difference, right? So then probability of E given F is 1 over 6 divided by 1/2, which is 1/3. So this checks out. Our intuition here matches the formula. Any questions about that? So I would say, generally speaking, this is going to be the main way that you compute conditional probabilities, is by, plugging it in the formula. So actually, before, when we were doing counting, we were just counting. When we started doing probability, we realized it's like kind of 2 counting problems where you divide them. And now we've got 2 probability problems where we divide them. Yeah. Yeah, so the probability that it's even, that it's equal to 6 and even is just the probability that it's equal to 6, because if it's equal to 6, it's already even, right? So yeah, this is going to be just 1 over 6. It's just the probability it's equal to 1 over 6. Or sorry, equal to 6, I mean. Okay. So let's do an example. Suppose we're now rolling a pair of dice. So what is the probability that the sum of the rolls is 4, given that at least one of the rolls is a 1? So if we use our formula, so on the bottom, we've got the probability that at least one roll is a 1. On the top, we've got the probability that the sum is 4 and at least one is a 1. I kind of think the bottom is easier to, well, I don't know. Maybe they're both easy to compute. So each of these, I would compute them by using the kind of ideas we built up for probability before, right? You think, how big is your sample space? And, how many things in your sample space satisfy the condition? So how big is the sample space for rolling 2 die? Yeah, 36, so 6 squared, 36. How many ways can I get the sum to be 4 and to have at least 1, 1? If you think about it, it's got to be like 1, 3. So yeah, we're computing the numerator now. So the only way you can have 2 dice that add up to 4 is like 1, 3, or 2, 2, or 3, 1. And these are the only ones that have a roll that's equal to 1. So the numerator should be 2 over 36. Right? Does anyone see what the denominator is? So it's going to be something over 36. So probability that you get at least one of them is a 1. You're going to have more than that because, in terms of how many possibilities are there, so you could have like 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Or you could have like 2, 1, or 3, 1, or 4, 1, or 5, 1, or 6, 1. So it turns out it's like 11. You can kind of write them out. 1, 1, 1, 2, 4, 1, 5, 1, 6, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. If you count up, there's 11. Right? So the answer at the end of the day should be 2 over 11. Right? Because when I divide this by this, the 36's cancel. Right? Any questions about that? Okay. Oh, sorry, I always miss you there. Sorry. For this one? Yeah, there is. So if you think about it, you can say, you can do a little bit of inclusion exclusion to get it a bit quicker. So you can say, how many ways, such that the first is a 1. Like, there's 6 ways to do that because there's 6 choices for the second one. You could also say, how many ways are there so that the second is a 1? There's 6 ways, which is concerning because this adds up to 12, which is not 11. But then you realize, oh, I counted 1, 1 twice. So the number of ways that both are 1 is 1. And so you should do like this plus this minus this. So it's 11. I'm not sure if that's any faster though or not. But if you had like, yeah, much larger number of possibilities, this might be a lot quicker. But any other questions? Okay. Okay. So one thing here which wasn't a coincidence, notice the 36 is canceled, right? That's going to happen a lot when you do these problems. Because if you think about it, yeah, the numerator is, like, if you're dealing with things with equally likely outcomes, the numerator is always going to be like something divided by the size of the sample space, and so is the denominator. So the size of the sample space is going to cancel. So note, when all outcomes are equally likely, So this is going to be, right? So by definition, this is just this, which if everything's equally likely, it just, you can replace this by this and this by this, and then you get cancellation, right? And it'll be like that. So this formula might be a little bit faster to deal with in those cases. Right? So you can assume that, like, if all outcomes are equally likely, then this is equal to that, right? Maybe one quick example. So I think this is also counterintuitive. Flip a coin twice. So you don't get to see the outcome. But your friend does. They tell you, so they say that there was at least one head. So given this, what is the probability of them both being heads? Okay. Actually, what would you say is, like, if you intuitively, any thought about? I mean, it almost seems like it should be like kind of a half or something, because I know there's one head, and then what's the probability the other one's ahead? It seems like it's like a half, kind of, right? But it turns out these things can be counterintuitive, so the answer to this is not a half. So to quickly do it, so let F be the event at least one head. E is the event that both are heads. Or let's say all the outcomes are equally likely, so we can use our formula from over there. Number of ways so you can get both of these happening over this. The top is going to be a quarter, because the probability that you have at least one head and both are heads is just the probability both are heads. The probability of getting at least one head is 3/4, right? Because you've got HH, HT, TH, TT. 3 of them have at least one head, which gives you a third. So you got to be careful with these things. We'll continue this next time, and we'll talk about this for a few more classes.